Hello, everybody. Thanks for waiting. We just had finished wonderful sessions on Bitcoin and blockchains by Professor David Say, and now we have this second research talk of the summer school. And our chair, second research talk is by Dr. Mayank Bakshi from Arizona State University, and our chair of the session is Shashank Vatedka. Professor Shashank Vatedka is a faculty member at IIT Hyderabad. He has a PhD from ISC, and he was a postdoc at INC. So that is something we all three share. Uh, Shashank, I hand over to you. Thanks.
Thanks, Ashish. Good morning, everyone. It's a pleasure to introduce Dr. Mayank Bakshi, who is the speaker for today. He's currently a research scientist at Arizona State University, and prior to this, he was a principal researcher at Huawei, and prior to that, he was a research assistant professor at INC, Chinese University of Hong Kong. He obtained his BTech and MTech from IIT Kanpur and a PhD from Caltech, all in electrical engineering. He works on a variety of topics and mainly on information theoretic security, network information theory, and sparse recovery. And today he's going to be speaking about sparse recovery. He's going to give an overview, including theory, algorithms, and applications. So welcome, Mayank, and the floor is all yours.
Thank you, Shashank, for the introduction, and thank you, Satyajit, for the invitation. It's a pleasure for me to give a talk here. Let me just take a couple of minutes to share the screen. I'm having some technical difficulties.
I will maybe interrupt you if there are any questions in between.
Okay, thanks.
All right. Hi, everyone. Apologies for the delay. There was a bit of a technical issue. So once again, I'd like to welcome Dr. Mayank Bakshi. He's going to be speaking about sparse recovery. The floor is yours, Mayank. If there are any questions, then please put them up in the chat box. I'll be monitoring it, and maybe I'll interrupt you, Mayank, in between, or we can take questions at the end.
Thank you all for waiting. I apologize for the delay. Okay, so today I'll be talking about sparse recovery, and I'll try to give an overview of sparse recovery, and I'll try to lead it through the work that I've done. I'll give a little bit of algorithms, a little bit of theory, and since I've also worked in industry, I will try to touch upon some of the applications of sparse recovery in practice, and hopefully that will help motivate, especially the students here, might get motivated to look at sparse recovery. Okay. So the big picture here, the big picture of my research, in fact, is that in general, for modern networks, there are many challenges. And some of the challenges are that the nodes are typically very highly limited by things like computational power and transmission power. But at the same time, when they're processing their data, even though there's a lot of data, often the data has a lot of dependencies, like maybe sparsity or correlation in time or across space. And we also have to worry about things like how to manage so many devices at the same time. Okay, so I've been looking at these problems from the point of view of signal processing algorithms and also information theory. And today I'll talk about the first two things mostly, which is how to enable communication and enable signal processing in these large networks by using sparsity and correlation in the data. Okay, so let's start with a little bit of motivation for sparse recovery. So imagine we have a very large cellular network. Okay, let's just think of a small subset of that, which contains a single base station and potentially many devices talking to that single base station. And okay, so if we think about this problem from just the point of view of wireless communications, we can think of the received vector at the base station as a linear combination of the transmitted vectors from each of the devices plus some channel noise. And if we formulate it as an equation, it could be something like y is equal to ax plus n. However, the challenge here is that potentially x contains many devices. So x is a vector of very high dimensions. And as we know, in general, in cellular communications, we can't afford to spend so much time allocating bandwidth to all the devices together. Luckily for us, it turns out that in cellular communications, most of the devices are off and only a few of the devices are on at the same time. And this can be also phrased in terms of a sparse recovery problem. Okay, the problem is, how do we encode or decode the communication from these devices without knowing a priori which of the devices are on? So the devices that are on, usually there would be a much smaller subset of the potential devices that could be communicating to this base station. And this enables the use of sparse recovery in this problem. I'll go into more details about how we apply sparse recovery for that problem. But I'll also talk about sparse recovery in the context of several other problems. So I'll talk about the following 4 problems. Most of the time, I'll be focusing on compressive sensing. I'll also touch upon the applications of sparse recovery in network tomography, which is a problem where we are trying to understand how network traffic is behaving. That is, maybe we want to understand what is the flow of how much is the volume of network traffic, and I'll show you how sparse recovery ideas are helpful there. And briefly, I'll also touch upon a problem called compressive phase retrieval and group testing. Okay, let's first start with compressive sensing. This is perhaps the simplest sparse recovery problem, and maybe this lets us build intuition into sparse recovery in general. Okay, so let's formalize the problem of wireless communication in the sparse recovery framework. So imagine we have n devices. Okay, think of n as a very large number, maybe tens of thousands of devices, and without knowing which of the devices are on, we have to think of the received symbol at the base station as some linear combination of the transmitted symbols from each of the devices. So here xi is the symbol transmitted from device I, and the coefficient a, this is due to either the code that is being used by the device, or it could be the effect of the channel itself. Maybe it's like the fading coefficient multiplied by the code parameter that is chosen by that device. So eventually what we receive is, at every time step I, we receive some linear combination of summation over j aij times xj's. Okay, and in the beginning, we don't know which of the devices are on. So our task is to decode this. Given this linear combination, we want to decode what are the xj's. Okay, and in general, we also have channel noise, so we have to add some ej as a channel noise parameter. Okay, so now we are going to bring the sparsity angle to this. So as we know, at any given time, only a few of the devices are going to be on or going to be active. We'll call that as k, and in general, we'll think of k as a number which is much smaller than n. Okay. There could also be, in addition to the noise on the channel, there could also be some noise from the devices themselves. So we have to take that into account as well. Okay. So, so now let's think of this as a sparse recovery problem in the following way. So this x, the vector that contained the transmission from all the different devices, let's call this the vector x. This is of length n, n corresponds to the number of devices. And what we know is that out of these n coordinates, at most k of the coordinates are non-zero. Okay? And what we get to observe is some vector y, which is hopefully of much smaller dimensions, much smaller dimension than n. And what we get to observe is this y, which is a linear combination of the entries from x. Okay, recall that this linear combination A corresponded to the effect of the channel as well as the effect of the transmission scheme that is being employed by these devices. Okay, so given this vector x, we know how to get y, right? We can just, given this vector x and in fact this matrix A, we can get y by just performing this linear combination. And the challenge is, how do we go from y to A? Okay? From this small dimensional vector to this large dimensional vector x. Okay? And hopefully, if we are successful, then we should be able to do it with m, which is much smaller than n. That is, we don't need tens of thousands of observations to be able to decode this x. And what we know is, just from a purely information theoretic point of view, we do know that m has to be larger than k. That is, the number of equations that we need has to be at least as much as the number of unknowns that are in this problem. Okay, and in general, it may not be the case that this vector x is exactly sparse, because these devices might have some noise, or there could be some channel noise which could be thought of as the vector x being just approximately sparse. So, but what we can guarantee is that this x will have only up to k entries which are high in magnitude. The rest of the entries would be hopefully much smaller in magnitude. And in general, we can call this, we can phrase this as A times x plus z is y plus e, where this z and e are the noise terms. The z corresponds to the approximate sparsity of x, that is, the norm of z is hopefully much smaller than the norm of x. And this e, you can think of it as the channel noise or the measurement noise for other settings. Okay. And finally, we want to solve this problem, and we want to obtain a solution which employs as few transmissions as possible. That is, this m is as small as possible, and we would also like that this matrix A is as sparse as possible. And the reason for this second point is that any non-zero entry in A corresponds to a non-zero transmission from one of the devices, right? So if a device is transmitting, then that means that that corresponds to a non-zero entry in the A matrix. And if there are too many non-zero entries, that means that devices have to transmit many times to be able to enable us to decode. And for practical purposes, we would also like the decoding complexity to be as small as possible. All right, so that was compressive sensing. We can also talk about general sparse recovery problems. In general, the sparse recovery problem can be thought of as mapping some sparse vector x or some sparse entity x using a linear or nonlinear operation A to hopefully a much smaller measurement vector y, such that we can recover x given the vector y. And we can recover x given the vector y under the knowledge that, or under the assumption that the vector x is sparse in some sense. And different choices of this operation A lead to different sparse recovery problems. Okay. The problem that we just saw, compressive sensing, that corresponded to a linear version of this problem, where this operation A of x was simply a matrix multiplication of x with A.
Hi, Mayank. This is Shashank here.
Yes.
Just a quick question. In the previous slide, so here the measurement noise E is A times Z, Is that it?
Oh, no. So I should have been a bit more clear. So there are two components which can be thought of as noise here. The first one is Z. Z can be thought of as the effect of the X vector not being truly sparse,
Sure.
right? So in general, X may not, even though I started with the assumption that X is exactly sparse, for many problems, it turns out that you can't assume that, but approximate sparsity still holds. That is, most of the entries are zero except, or close to zero except a few of them. And the second term, E, is the measurement noise. So even if X was sparse, even if Z was zero, you could still have some noise which is due to the measurement process itself.
Okay.
That's
So effectively we have A times X plus Z plus E. Is that?
yeah, you can, okay, yeah, I could have
Maybe
written it
that's
like
one
that.
way.
Yeah,
Okay.
yeah,
Okay. Great.
yeah.
Thanks. There's one more question in the chat.
Mhm.
So is
Mhm.
K always a fraction of N, or can K be like square root of N?
Yes, K can be, yeah, it depends on the problem. Yeah, you can you can make K scale with N as well. You can be like order little of N, or you can be some constant times N or square root of N. Anything is allowed. But the solution that we get might depend on the scaling of K with respect to N.
Okay. Okay. And the general assumption is that A is exactly known. A and K are, I guess, known. Is that it?
For some problems,
Okay.
yeah, but yeah, for the simplest problems, we assume that it is known, but there are certain problems where we don't even know what A is, or we have some partial knowledge about A.
Okay. And K is known.
Yeah, we assume we assume that we at least know an upper bound on K,
Okay.
so that we can. Actually, it turns out that even if you don't know K, you can do things like maybe you first try to solve for a given value of K and then gradually increase the value of K until you get an acceptable solution.
I see. Thanks.
Okay, let me now talk about the second problem, which is network tomography. Okay, so here the challenge is, one of the ways in which we can think of network tomography, or one of the applications of network tomography, is the following. So suppose we are given a network where we are trying to understand the network traffic in some way. Okay, so maybe there's a bottleneck link in the network, and we are trying to figure out which is the bottleneck link and how much is the delay on this bottleneck link. And in general, it's not feasible to actually go and measure every link in the network one by one. If we are able to do that, then certainly we can identify the bottleneck link, but practically that's not feasible. So one way to overcome this is to send test packets from different source nodes to different destination nodes in the network, and you observe the end-to-end delay of these test packets and try to infer the delays on individual links. And again, it turns out that if we assume that the number of congested links is much smaller than the overall size of the network, then then we can apply sparse recovery ideas to recover exactly what are the links and what is the amount of delay on the congested links. Okay. Now, another problem of sparse recovery is a phase retrieval problem. Here, unlike compressive sensing and unlike the network tomography problem that I talked about, it's not a linear problem. Okay, so here the goal is to recover recover something like the 3D information about an object just from intensity measurements. Okay, so we try to recover both the phase as well as the amplitude of a certain vector just looking at the amplitude of the observations. And it turns out again that if the underlying vector is sparse, then we can do this under certain assumptions. And finally, the last problem that I will talk about is group testing, which is also a nonlinear problem. And in the this is especially well motivated in the current day when we have a pandemic. So the problem is as follows. Suppose we have n items or n samples. What we know about these samples is that some small fraction of these items are defective or they are infected. Okay, so imagine that in a large army, maybe a small fraction are infected with a certain disease. And we want to identify who are those people which are infected. Clearly, one way is to just go and test the blood from each person one by one. But that turns out to be very expensive, especially if it's a pandemic. Then you can't hope to uh, test everyone one by one. So one way to overcome this is using group testing, which is by using pooled tests. And the idea here is that instead of sampling one by one, you could group together samples, and if the group contains an infected person, then this test outcome would be positive, which is denoted by the red group over here. And if the group contains no infected people, then the test outcome would be negative. And group testing enables us to perform pooled tests like this and recover the set of infected people by using very few number of pool tests. So again, this is a nonlinear problem, because if you think about the output yi from any test, we can think of it as a Boolean operation. So the Boolean operation here is a OR operation, where the OR runs over all the items contained in that pool. And here xj is 1 if the item is defective or if the person is infected. And the outcome is 1 if any of the items is defective or any of the people in the test is infected. So given all of these tests, it turns out that by using group testing, we can actually recover the set of infected people. Okay, and in my work, I have looked at all of these problems from the point of view of algorithms, and I've tried to come up with fast and efficient algorithms for these problems. Okay, so before going into details, let me just, since there are many students here, let me try to give some intuition as to why sparse recovery is even possible. Why is it that we can perform sparse recovery? So let's first think of a simple puzzle. I call this the gold bar puzzle. So here the setting is as follows. So suppose first that there are 5 people, and everyone has a stack of gold bars. And in an honest world, everyone has gold bars of the same weight. Okay, so let's say the weight is 100 grams each. Now suppose one of these is a thief. We don't know which of these is the thief, but the thief steals an unknown amount from each of the gold bars. And the question is, how do we identify the thief? Clearly, one way to identify it would be to just sample, or just weigh gold bars from each column one by one, and then we would be able to tell which is the thief. Is there a better way of doing it? Is there a way which uses fewer number of measurements? Okay, so how do we design measurements for this problem? That is the puzzle. Okay, so let's think about this. So one way to do this would be, first of all, we could just take measurements from all of the measurement. We could just take a measurement which includes 1 bar from each of them. Okay, so suppose the thief has stolen 10 grams from his stack, from each bar, then the measurement would be 490 grams instead of 500 grams, which it should be. Okay, so this tells us that the measurement is this tells us how much the thief has stolen. And now the second step would be to identify who is the thief. And here is a nice trick which lets us identify which is the column which corresponds to the thief. So first, we could take one gold bar from the single column, from the first column, 2 gold bars from the second column, 3 from the third column, and so on. This way, the amount that is stolen by the thief, that gets weighed by the column number of of the thief. Okay, that is the amount that is stolen is weighted by these coefficients 1, 2, 3, 4, 5, and looking at the outcome, we can now immediately infer which is the thief. Okay, so for this example, perhaps you can see that if the outcomes are like this, minus 10 and 40, then this tells us that the thief should correspond to x4 because the ratio of these two is 4. Okay, so that lets us figure out a thief using just 2 measurements instead of instead of 5 measurements, which would have been required if you would not use the sparsity assumption here. Okay, the sparsity assumption here is that out of these 5, only one of the columns corresponds to the thief. Okay, so this brings us to the first idea behind sparse recovery. So in general, if we want to perform measurements, and if we want to perform measurements in an efficient way, then we should perhaps look towards measurements which are more structured rather than just purely random measurements. Okay? And so this was one example of more structured measurements. Now let's look at a more complicated setting where maybe there are more than one thieves. So in general, you could have a setting where there are, let's say, 2 thieves out of 5, and it's not clear a priori that the previous scheme would generalize, because the following might happen. So if we choose some subset of columns to perform this original idea on, then if that subset contains more than one thief, then the previous scheme doesn't work, because we get something which doesn't look like it immediately gives us the solution. Okay, so even though we are using the same idea as earlier, it's not giving us any direct answer. However, if we randomly end up choosing a subset which is nice in the sense that it only contains a single thief, then that subset has this property that we can identify which is the thief by looking at the columns that correspond to that measurement. Okay, so this green subset corresponds to the last 2 measurements, and as you can see, looking at the green subset, we can immediately figure out that the thief corresponds to column 3. Okay? So hopefully, if we have many measurements, then we can use some of the measurements to identify a few of the thieves. Okay? Now, once we identify a few of the thieves, then we can reduce our problem by subtracting out the effect of the thieves that we have already identified. And after we subtract out the effect of the thief corresponding to column number 3, we are now reduced with a problem which has just one thief out of the remaining 4 columns. And now we can apply the initial idea again, and turns out that now we can solve the problem iteratively. Okay. So this brings us to the second idea behind efficient algorithms for this problem, which is to start with start the decoding process in a way so that we can apply structured measurements, but we don't hope to solve the problem at one step, but maybe iteratively we can try to solve the problem by trying to reduce the problem to a simpler problem. Okay, so this is the second idea, which is we try to somehow peel away the effect of the measurements which we already know how to solve, and then once we peel away the effect of those measurements, we can solve the remaining measurements, solve for the remaining measurements. Okay, now let's so let me try to formalize this in a way which will apply to more general problems. So we can think of the measurement structure as a bipartite graph, where the left-hand side of the bipartite graph corresponds to the vector x. This is the sparse vector that we are trying to reconstruct, and and the right-hand side corresponds to the measurement outcomes. So this yi's are the values in the gold bar example. These yi's were the weight of the gold bars coming from these columns. So the green one was the green columns, and the yellow, the Y2 was the yellow columns. And recall that this Y1 was a singleton in the sense that Y1 corresponded to exactly one thief, whereas this Y2 was a multiton, that is, it corresponded to multiple thieves. Okay, and in this measurement graph, we draw an edge as long as the x1 appears, or is it the x1 corresponds to some non-zero entry in the linear combination y1. So x1 is connected to y1, x2 is connected to y1, and x3 is connected to y1 because, as you can, because the first three columns, they appear in the first measurement. Similarly, the last four columns, they appear in the second measurement. So x2 up to x5, they are connected to y2. Okay. So, and we can think of the decoding process as picking and peeling over this bipartite graph. The first step was to try to figure out a singleton in the graph. Okay, and looking at the looking at the first measurement outcome, we could identify this singleton. And after we subtract the effect of the first measurement of the thief number one, then we are left with a subgraph which contains a new singleton. And now we can apply the same decoding idea to this subgraph, and turns out we can solve for the whole problem. Okay. So now I'll try to quickly go over how this is applied to compressive sensing. Since I'm running out of time, I'll not spend too much time on the actual details. Before that, let me just give a quick overview of compressive sensing itself. So, so this compressive sensing has been around for a while. It was introduced by Candace et al. In 2005. And initially, the first works relied on Gaussian random matrices. That is, the matrix A was chosen using Gaussian random entries. And it was shown that you can decode as long as the number of measurements is at least order k log n. And the breakthrough here was that we don't need to solve it by using very complicated methods. We only need to do something like linear programming to be able to figure out the sparse vector x, which corresponds to the measurement outcomes y. And one of the properties that enables this breakthrough is this property called restricted isometry property. This says that this measurement matrix A, as long as it satisfies the property that all sparse vectors, they are roughly mapped to y values which are of the same norm, then this measurement matrix can be used to decode sparse vectors. So for a given measurement matrix A, as long as all sparse vectors, all k sparse vectors are mapped to y values which are of the same norm or of proportional norm, then that matrix A can be used to perform compressive sensing. And there's a whole lot of work on compressive sensing. Some of the important algorithms are things like orthogonal matching pursuit and so on. So I would like to highlight here one thing. So there are basically the first works which looked at zero error compressive sensing. That is, compressive sensing with guarantees that for every k sparse vector x, the same matrix A should be able to work. That is, the same matrix A should give you the guarantee that you can recover the vector x given y. However, it turns out that's not necessary. That's not the only way to phrase compressive sensing. You can also talk about high probability compressive sensing. That is, given a vector x with high probability over the choice of A, you should be able to recover that vector x. And the work that I have done, this uses this relies on this framework, that is, given a k-sparse vector x, if we relax the decoding criteria to the following, that is, the probability of correctly decoding the matrix, correctly decoding the vector x by the matrix A, if we just demand that this probability is close to 1 rather than exactly 1, then it turns out that we can not only we can decode efficiently, but we can decode using fewer number of measurements than what Candice et al. Require. In fact, the number of measurements required is now linear in k rather than proportional to k log n. Okay. It also has the nice properties that we can decode with complexity order k, and the matrix A is a sparse matrix. That is, the number of non-zero entries in A is also proportional to n. Okay, even though this matrix A is of size m times n, the number of entries is much smaller than m times n. So maybe in the interest of time, I'll skip the details. I'll just highlight that this is the like if you think about lower bound on the comprehensive sensing problem, clearly order k is a lower bound on both the decoding complexity as well as the number of measurements, because if we have k unknowns, we need to have at least k equations to solve for them, and if we want to output k real values, then we should have at least order k decoding complexity. And our work achieves both order optimal decoding complexity as well as order optimal number of measurements, if we think about those. Okay. So the main idea behind our work is, again, using this bipartite graph to formulate the compressive sensing problem. And just like the gold bar puzzle, we can use this bipartite graph to design the measurement matrix by assigning different weights for different edges in this bipartite graph. So, for example, here, this entry A11 corresponds to the edge x1 to y1, and the way this A11 is chosen, that has a certain structure, but essentially the idea is very similar to the gold bar puzzle, where we try to first design the bipartite graph in a way that we can decode a few of the singletons with high probability. And then once we have decoded those singletons, we try to peel away the singletons and we are left with a smaller problem. And we try to identify singletons in the smaller problem and then iteratively proceed until we can solve for all the non-zero values. So since I'm already running late, I'll skip the details for this problem because there are also other problems that I want to talk about. Okay. So one of the but one thing I would like to highlight here is that so one question that might arise is why is that this process works? Okay. So one nice property which enables us to perform this peeling and decoding over the peeled graph is the expansion property. So this says the following. So if the graph satisfies this property, that the number of neighbors of any small subset S is at least some constant times the size of that set, then that allows us to prove that there are many singletons in the graph at every step. And once we know that there are many singletons, then we can show that the decoding will can proceed, and decoding will in fact only terminate once we have identified all the singletons. Yes, and the proof of this is very similar to ideas from expander graph. So maybe if you're familiar with that, you can understand this. But don't worry if you are not familiar with that. Okay, so let me skip all of this and move to network tomography. So the first problem problem of network tomography is the following. So we are given some network where some of the nodes are, some of the edges are congested, and we are only allowed to perform end-to-end measurements on the network. That is, we can't perform link by link measurements. We can only perform end-to-end measurements on this graph. Okay. So here we can one example of an end-to-end measurement would be the following. So let's consider this green path over here. Okay. Suppose we send a test packet over this green path, then the overall time taken for this test packet to go from node V1 to node V5 would be simply a sum of the time taken over all of the links. And that can be expressed as a linear combination. Okay, so first of all, the links which are not visited at all, they would correspond to 0 weight. But the links which are visited, they would the weight of those would correspond to the number of times those links are visited. So, for example, this link over here, this is visited twice, E5, so that has a weight 2. So what we get to observe is just these end-to-end delays, which are linear combinations of this edge of the whole edge delay vector. And if we assume that this edge delay vector is sparse, then we can immediately see that you can apply compressive sensing ideas and recover this end-to-end this edge delay vector if nice properties are satisfied. Okay. So some of my work has looked at this problem, and it turns out that we can in fact design the measurement matrix here. We can design the end-to-end delay, end-to-end measurement process in a way that allows us to find the congested links for any graph by just reducing it to a compressive sensing problem. Okay. The second, so this was the problem of network delay tomography. Just to differentiate it from the next problem that I'm going to talk about. Here, the goal was to infer the delays on each link. You can also talk about other tomography problems on networks. Another problem which I've also worked on is the following. So suppose we are given a network and we are interested in measuring network characteristics. Okay, for example, we may want to figure out what is the end-to-end traffic flow from different sources to different destinations. Okay, so for example, in this network, maybe user 1 and user 2, they are trying to get traffic from many different sources such as Amazon Prime, YouTube, or Netflix. And as a network designer or network optimizer, we want to figure out what is the traffic volume for each source destination pair. Okay, so as you can see, potentially there are many source destination pairs, and the challenge here is that we cannot directly measure the source destination traffic. Excuse me. So it turns out that if we want to directly measure the source destination traffic, then we have to perform many expensive operations. One way to do it is to actually go and look at each node and examine the packets that pass through that node, look deeply into the packets, perform deep packet inspection on each packet, and then you have to apply. Then you have to maintain a counter for every source destination pair, and that would enable us to find. That would enable us to measure the source destination traffic for every source destination pair. However, in practice, this turns out to be very expensive, and this is not done almost anywhere. So what is available is, though, sometimes we get to see part of the source destination traffic. That is, maybe for some SD pairs, we know what is the traffic volume, or we can also observe the link traffic. It is easier to observe what is the total amount of traffic passing through any single link. For example, over this link, we may know what is the total traffic without knowing what is the traffic for different SD pairs. Excuse me. Okay, so here, as an example, maybe we can directly measure the traffic from this source to this destination, and we can also measure the link traffic on different links in the network. And the challenge here is that can we recover the source destination traffic from whatever data that we have, that is from the subset of link traffic, subset of SD traffic and the link traffics that we get to observe. Okay, so let's formulate this problem. So first, what we want is the traffic flow matrix. Okay, so this traffic flow matrix X can be thought of as a matrix which runs over all the SD pairs. In general, they would be V cross V, where V is the set of all the vertices. And what we get to see are link flows. Okay, so we only get to see the total traffic volume on each of the edges. And this can be thought of as a linear function of the original traffic flow matrix. Okay, so what we have is order of V square unknowns, which are these entries of X. And what we get to see is just order of E equations. Okay, and in general, it turns out that for typical networks, this E, the size of the edge set it scales with the number of vertices, and it doesn't scale with the square of the number of vertices. So we have much fewer number of equations than we have unknowns, and that perhaps tells us that maybe we can apply sparse recovery over here. And if you're familiar with recommendation systems, then maybe this reminds you of this, of recommendation systems as well. So there we have, again, we have a matrix where we want to recover the entries in the matrix, and we don't get to see all the entries in the matrix as it is, but we get to see some of the entries, and our goal is to reconstruct the other entries. For example, here, maybe you get to see the entries which have certain numerical values associated with it, and you want to infer the other values. And unless we know some additional information about this problem, we can't hope to solve this, right? So, like for example, if you have a matrix recovery problem where you have an unknown X and you observe some linear function Y, then clearly if the length of Y is smaller than m times n, then there's no guarantee on recovering X. However, it turns out that if the matrix satisfies a sparsity-like property, which is the low rank property, then we can in fact hope to solve this problem. Okay, so it turns out that if X this measurement matrix A satisfies something like the restricted isometric property, then we know that we can solve for X by using something like nuclear norm minimization over the matrix M, subject or over all matrices M, which are consistent with the measurements that we have seen. And the intuition for this is very similar to the compressive sensing problem. The rough intuition is as follows: if the matrix has, if the rank of the matrix is smaller than R, this is equivalent to saying that the singular values of the matrix are sparse. Okay? So if we consider a singular value decomposition, then, sorry for that, then this, the singular values of this matrix, this is a vector which has very few number of non-zeros. In fact, if the rank is R, then at most R of them are non-zeros. So once we have this property, then we can try to relate this to compressive sensing. And it turns out that by using similar ideas and more complicated analysis, one can argue that you can do nuclear norm minimization and recover the original matrix. Okay, so you might wonder why this makes sense for the problem that we started with. So it turns out that the rough heuristic for this is the following. So X can be thought of as as containing two things. So the rows are the identity of the users, and the columns correspond to the demand patterns. That is, what percentage of the traffic from a certain user is going to YouTube, what percentage is to Netflix, etc. And empirically, it has been observed that even though different users have different might have different demand characteristics, actually we can think of those demand characteristics as just consisting of linear combinations of certain basic demand patterns. That is, the fraction of traffic going to different servers can be thought of as a linear combination of certain unit demand patterns. And once we have the low rank assumption, then we can empirically we can show that encouraging sparse solutions for this problem gives us a satisfactory solution. That is, it gives us a reasonable amount of accuracy in practice. There are a few challenges here, which are specific to the network traffic problem. First of all, how do we find the low rank solutions efficiently? Given the size of this problem, it is important to find efficient solutions. So it turns out that finding the lowest rank solution is NP hard in general. So we have to use certain relaxations to figure out what acceptable solutions are. Secondly, in general, the traffic data may not be just two-dimensional. You could have multiple dimensions, like you have the spatial dimension, the source, and the destination as the spatial dimensions, and you could also have dependence over time. So we have to look at things like low-rank tensor recovery, which is even more challenging. And yeah, I've worked on both of these. In the interest of time, I'll not spend time on this. Okay, let me just, since I'm running out of time, let me quickly talk about the two other problems. Okay, so the third problem is compressive phase retrieval problem. Here, the problem is as follows. So we are interested in figuring out an unknown vector x, and again we are assuming that this vector x is sparse. It has only k non-zero values. However, what we get to observe are not the values of x directly. What we get to observe are just the absolute values of linear combinations from x. Okay? And here we can even think of x as complex values. So if x is a complex vector and we get to observe only the magnitude of the linear combinations of x, then recovering x in general is not possible. However, what we can hope for is that we can recover x up to a degenerate global phase. That is, we can recover x up to a global phase, which cannot be resolved. Okay. So the problem is like this. Okay. So we are given this vector x. We are allowed to perform measurements on this vector x by multiplying it with a matrix. This gives us a linear. This gives us an intermediate measurement matrix, a measurement vector p. And what we get to observe is just the intensity, that is the absolute values of entries from B. And how do we recover x up to global phase given this vector y? So this is the problem of compressive phase retrieval. And again, it turns out that if we know that the vector x is sparse, then we can perform this operation by using a small number of measurements. Okay. So again, the idea here is very similar to the compressive sensing problem. So again, since I'm running out of time, I'll skip the details here. Okay, finally, let me just talk about the group testing problem. So here, as I mentioned here, the group testing problem is a nonlinear sparse recovery problem. Okay, so we think of a group testing problem as follows. So first, we are performing tests of the following kind. Okay, so here the columns correspond to. Sorry. Yeah. So imagine the following. So we have columns corresponding to the different items that or different entries that different entities that we are interested in testing, and the rows correspond to different measurements that we can perform. Okay, and a one corresponds to one in any row corresponds to this test containing the the item corresponding to this column. Okay. So for example, if this is this column corresponds to an item which is not defective, then every test that includes this um, every test which includes this and not any other defective item, that will give us a zero value. But if a test contains a defective item, which is the second, this red test over here, then this will give us one value. Okay. So the goal is to recover, to first of all design this testing scheme, and secondly to be able to decode all the defective items given the set of negative and positive outcomes. Okay. And again, we can show that by using similar ideas as the gold bar puzzle, we can define, we can design measurement matrices which satisfy the property that we can that we can find those defective items using a small number of tests. In fact, order optimal number of tests, and we can also decode it with order optimal decoding complexity with very high probability. So that's a very quick overview of the group testing problem as well. Okay, so since I'm running out of time, I'll just quickly summarize. So so what we looked at in this talk is basically a way of looking at sparse recovery problems using bipartite graphs. So the first step is to design good bipartite graphs, which enable us to perform structured measurements. Okay? So the example that we saw that showed us that if we can design graphs where we can do step-by-step decoding as follows. First, we try to decode the items that we the entries that we can decode in one step, and we try to identify those. So these correspond to the singletons. Next, we try to peel away the effect of those, and once we are left with a smaller problem, we can decode the remaining items. So this gave us a way of performing iterative decoding for this problem, and what we end up as a result of this iterative decoding process, in general, we can come up with algorithms which are not only order optimal in terms of the number of measurements, but also decoding complexity. Okay. So yeah, let me skip this. Okay, so just a few few things which I'm looking forward to in terms of research direction. So first of all, so this gave us a framework for exploiting sparsity for network applications, and what would be interesting is to apply this to other settings. For example, in multiple access problems, we often have to worry about things like being able to correct errors in addition to just figuring out which are the active devices. So it would be useful to combine this with things like error correction. There are recent works which look at massive random access problems, which apply compressive sensing, and those seem very promising. It's also interesting to look at different measurement models and maybe different sparsity models. Maybe for certain problems, it also makes sense to talk about the energy consumption, and those could lead to different metrics in addition to just the number of measurements and the number of decoding steps required. Maybe we also need to look at ways to minimize the overall energy in transmission as well as decoding. And there are a few works which have started to look at machine learning methods, and sometimes these give us faster algorithms, and we can conceivably also think about other sparsity models that are motivated by applying machine learning to this problem. Okay. So that's all. Thank you.
Yeah,
I'm happy to take questions.
Thanks a lot, Mayank, for a very interesting talk. So there's one question by Neha. She's asking, is there any other important property besides the restricted isometry property that the measurement matrix has to satisfy for the retrieval algorithms to work? And for the non-linear cases, is there any such property that the matrices have to satisfy, or any?
Yes. Okay. That's a good question. Yeah. So I did not focus explicitly on the properties that are needed. Yes. So for the original compressive sensing problem. Yes. For the original compressive sensing problem, it turns out that if we want the uniform guarantee, that is, if you want a guarantee that the same matrix A should work for every vector, every k-sparse vector X, then we do need this restricted isometry property. However, if we relax this requirement, then we don't always need it. In fact, the reason why we end up with faster algorithms is because we bypass the restricted isometry property by allowing for a small decoding error. Okay, and and moving on to the second part of the questions about nonlinear sparse recovery problems. So we do need some conditions. We do need something like restricted isometry property for those problems. For the matrix recovery problem, for example, something like the matrix version of the restricted isometry property is known. For the compressive phase retrieval problem, it's not, as far as I know, there are necessary and sufficient conditions, but I don't know exactly if those match for recovery to hold. And for the group testing problem, again, there's a distinction between zero error group testing and high probability group testing. It turns out that for the zero error group testing problem, something corresponding to the restricted isometry property is known. It's called disjunctness and distinctness property of the matrix. So as long as the matrix satisfies that property, it's known that you can that matrix can be used to perform group testing for every k-sparse vector X. I hope that answers the question to some extent.
Okay, thanks. So Lakshmi Prasad says, thank you for a very nice talk. Can you tell us how the approximate sparsity is handled in such problems?
Okay, so all right, so yeah, so actually, it turns out that the work that I presented, the approach that I presented, which is the iterative decoding approach, that doesn't always give us good solutions when the input is approximately sparse. You have to do a little bit more work to be able to show that the effect of approximate sparsity doesn't blow up the propagation, or doesn't let the error from decoding propagate over the iterative decoding process. But in general, if you forget about the approach that I presented in this talk, the general way to worry about approximate sparsity is to look at the linear programming solution to this problem. So given the measurement outcome y, one way to solve this is to look at a vector x which minimizes a L1 norm of all things which satisfy the equation y is equal to ax plus some noise term, and that extra noise term shows up in the regularizer in this linear programming formulation. So the approximate sparsity, the effect of the approximate sparsity is to end up with a non-zero regularizer term, and what we hope is that we want to minimize in order to get a sparse solution or approximately sparse solution, we hope to somehow try to minimize some sort of norm of x plus this regularizer term. And there are theoretical guarantees as well on this problem. So you can show that as long as the approximate sparsity is bounded, that is the norm of the norm of the vector z is small, then you can recover the original vector x up to a small error as long as the matrix satisfies the restricted isometry property.
Thanks. Any other questions? Maybe just one quick question from my side. So I guess in many applications like the cellular communication application that you mentioned, and maybe even a traffic flow, I guess one could think of it, one could perhaps solve it in a slightly different way, wherein you adopt perhaps a sequential approach. So I guess in all your works, you're fixing the number of measurements beforehand, right? Are there versions where you maybe take more number of measurements, perhaps you don't know what k is or something of that sort, and then there's a stopping point beyond which you can recover it, recover this? So.
Okay, all right. So actually, yeah, one way. Let me try to rephrase what you asked. So I think what you're asking is that is there an adaptive way of performing these things, and like what is the effect of adaptation?
Yeah.
So it turns out that so it depends on the problem setting. In the wireless communication example, adaptation might not be desirable in the sense that you might not want to adaptation in this setting means that you have to retransmit. You have to transmit, then you have to wait for the transmission from the base station and retransmit. So that takes actually more time. But in certain other settings, it turns out that adaptation is not only is it possible, but it leads to better solutions. So in group testing problem, I didn't talk about more details of that problem. So in the group testing setting, let me pull up that slide. Yeah. So here it turns out that if we design this measurement matrix a priori, then that is suboptimal. It turns out that you need more number of measurements, but you could conceivably think of a different process where you are designing this matrix one by test by test. That is, you design one row of the matrix, you look at the outcome. If you see that there are no defectives, no infected people, then you don't need to consider the items that you have already included in this test. So you just leave those out. So you don't have to measure those things again. So this way, you can actually save on the number of tests. So adaptation here is actually beneficial.
Yeah, thanks.
Yeah. So it depends on the actual practical setting whether adaptation is useful or not. If we just worry about the number of measurements as a parameter, then yes, that would be adaptation is in general useful, but whether or not that can be applied to the practical problem is it depends on the actual problem.
I guess there are no other questions. So, in the interest of time, perhaps we can wrap up here. So, let's thank Dr. Mayank once again for a very nice talk. Yeah, Satyajit.
Yeah, thanks Shashank, thanks Mayank. Very rich set of ideas. Now we will move to the industry session. So I request all participants to move to the next session, Sankhya Lab session. Thank you. Yeah, so